Okay, looks like we got everything set. All right, just one moment. Okay. Well, let's get going tonight. Talk a little bit more about convergent series of analytic functions and get a little bit more information about how convergence results carry over to functions and what analytic functions have to do with convergent infinite series of functions. So if you recall from last time, here, let's jump back real quick. Um, if you recall from last time in the beginning of our discussion, we talked about convergent sequences real quick. We just reminded ourselves of what that meant. We talked a little bit about convergent series, which of course just comes from a convergent sequence of partial sums. And then we talked a little bit about absolute convergence, how absolute convergence kind of let us bring over some results from Calc 2 into the complex setting. Then we went on a little bit, described the notion of uniform convergence, which was a slightly stronger notion than pointwise convergence. It just boiled down to converging at a uniform rate. And the picture of something that doesn't do this is something like a sequence of parabolas. That is like the middle will get close to 0 like this in this example as n gets big at a very quick rate, while the outside parts get close to 0 at very slow rates. That is, the further you go out, the slower they go. And so there's no way to bound how slowly they go. They go as slowly as is possible. You know, pick a slowness and they go that slow at least. In contrast to things where we can actually bound the convergence to the eventual function in nice little epsilon bands. So that gave us uniform convergence, and we were like, well, what do we care about this for? Why does it even matter? And the answer came about after we talked a little bit about some useful lemmas here, some additional pieces, the Koshi criterion. We got to a much more interesting and useful piece of information that told us a lot about why we care about uniform convergence. And the answer in this case was because uniform convergence preserves continuity. That is, the uniform limit of continuous functions is continuous. And that's a pretty big old deal. So what we'll start today with is a relatively pain-free little result called Weierstrass's M-test. It is a pretty useful test, I would say. It is a really good, it makes sense and it's easy to use. So Theorem 3.1.7, Weierstrass's M-test, it's a really good result to have in your pocket. You can use it all over the place, not just in this class, but in other contexts in mathematics. It's just a good one to remember. So what we'll start with is Gn, a sequence of functions defined on a set A contained in the complex plane. And we're going to suppose that there's a sequence of real constants m sub n greater than 0 or equal to 0, such that both of the following conditions hold. Each of the functions Gn is bounded in modulus by Mn for all z. That is, these guys, these Mn's just tell you how big the G's get, right? Okay. And the series of these Mn's converges. Okay, that means that as you sum them all up, you get a number out as opposed to getting something undefined. Then what we get is, this is the part that obviously makes sense, is that the sequence or the series of functions converges. And not only does it converges, and this is the big deal, absolutely and uniformly on A. Okay, kind of a big deal. So what this says is it's basically like a comparison test, essentially. All you really need to think about, if you want, is that a sequence of real constants is indeed a sequence of complex valued functions. That is, every constant defines a function. It maps a complex number to that constant. Every number gets mapped to the same constant. They're constant functions, right? So what we're really saying is that in modulus, at least, these functions are bounded, and the series is essentially termwise bounded by the terms of a convergent series, right? And this is, of course, again, the way people like to kind of say wire stress stem test is that you're using, like a sequence of constants to bound like a sequence of functions, or, and then you get convergence of series, right? Comparing a real series to a series involving functions, but realistically, because constants define functions as well, we're just basically doing the comparison test. Nothing that crazy. The nice piece is the absolutely and uniformly part right here. Namely, this this will give us a lot of the properties we want, like preserving continuity and so on. In particular, if you know that for these GNs, then you'll get that for the resulting function. Let's just run the proof. It's real simple. So since the series of the MNs converges, for any epsilon bigger than 0, there is a capital N, such that for all little n greater than or equal to big N, this implies that, and this just comes from the Koshi criterion, just that, or if you want to actually, just from the definition of convergence, that the sum from k equals n plus 1 to n plus p of mk is less than epsilon. Now, you don't need absolute values here because the MNs are all greater than or equal to 0. If you're trying to see what's going on in this situation, just think about, I'm just drawing an arrow there poorly. If you took, say, like the sum from k equals 0, or I guess I should probably go from k equals 1, right? Yeah, k equals 1 to n plus p of mk minus the sum from k equals 1 to, let's just go up to n of mk, an absolute value. This is just going to be equal to, well, because we don't need the absolute value bars, and we can get rid of the first, n terms of this sum right here, right? We just get sum from k equals n plus 1 to n plus p of mk. That's this piece right here. Oops, bad drawing. That's that guy, yeah? So if this part's less than epsilon, then certainly this guy is as well. So that's all that's going on with this statement. And so this will hold, of course, for all p equal to 1, 2, 3, up, so on and so on, right? Okay. That is, for any epsilon, there exists some big N, so that this holds for any choice of p. Okay, there you go. That is, after some n, everything is close enough and stays close enough. So let me get back to my highlighter now. Thus, for such little n's, we have that these GKs, in the sum of these GKs guys right here, right? So this is, once again, the exact same thing, but now we're putting the G's, right? Instead of the M's, just do the exact same thing with G's, GK of Z instead of the MKs, right? This guy is the sum of all of them, definitely by triangle inequality, less than these guys, right? Sum of the absolute values. That's fine. Okay. And that, by our assumption right up here in 1, says these guys are less than the MKs. But hey, we just went right here and said that we can make those as small as we want. for some appropriate n, right? So by the Koshi criterion, which we just talked about again, that nice little result before, if you want to go back, we can recall it. By the Koshi criterion, this little piece right here, series converges uniformly if and only if for each epsilon there's an n such that exactly what we just got happens. So that's an if and only if. And so naturally, what we've just gotten is our desired result. We got convergence, both absolute and uniform. Nice. So pretty smooth little test. Basically, if you can bound the terms of your series, these functions, with real constants so that the series of those constants converges, then you can get absolute and uniform convergence. Kind of nice. Okay, now on to something involving contour integrals, which have played a very central role in everything we've done so far in this class. Gonna lower my chair a tiny bit so I can write easier. That's too low. Yeah. Actually, it's even worse. Okay, there we go. So let's get going there. All right, so proposition 3.1.9, something to do with contour integrals, makes our lives more interesting. We'll be able to bring results like Koshi's theorem into the mix. So proposition 3.1.9, we're going to take gamma, a curve in a region A, and we'll let Fn be a sequence of continuous functions defined on the image of gamma, that is on that curve, and which converges uniformly to a function f on the image of gamma on that curve. Then what we're saying is that the contour integral about gamma of these fn's converges to the contour integral about gamma of f. That is, the sequence of contour integrals converges to that contour integral. Kind of natural. Another way of saying this, if you want to, is that the limit as n goes to infinity of the contour integral of gamma of fn is equal to the contour integral about gamma of the limit as n goes to infinity of these fn's. Right? So you can exchange the limit and this contour integral in this case. Oh, okay. So uniform convergence not only preserves continuity, but allows you to commute limits with contour integrals. That's useful. That will turn out to be a pretty big deal for us. Namely, we'll be able to use facts from Koshi's theorem to our advantage. All right, fair enough. Let's get on to the rest of it. And similarly, if you have a series, sum from n is 1 to infinity of gnz, converges uniformly on gamma, then we can interchange infinite sums and integrals. So basically the exact same statement right here, but with sums instead of these limits, right? Why does this work? Well, it's obvious because this this infinite sum right here, right, is just defined in terms of a limit. So this is really saying less than this first statement, but it's just saying a subcase in a more specific form. So that is the integral about gamma of this series, this infinite series, is equal to the infinite series of these integrals about gamma, right? Oh, okay. Nothing fancy. It's just this statement up here again, but said in a slightly more restricted context. That is when the terms of these fn's are given by partial sums. Okay, fair enough. All right. So for a proof, the function f is continuous by proposition 3.1.6. Okay, what is that? Why is that? That's that last result we went over last time, if you guys remember. It says that the uniform limit of continuous functions is continuous. So, very naturally, since we're starting off by assuming that we have uniform convergence for a sequence of continuous functions, obviously that limit, the uniform limit of some continuous functions is indeed continuous as well. Okay, so it's integrable. That is, it makes sense to do the integral about gamma of f. Fair enough. So given an epsilon greater than 0, we can choose a such that for little n bigger than capital N, we have that fn z minus f of z is less than epsilon for all z on gamma. Okay, now notice. Okay, so let me make sure. They've made a mistake. Oh, textbooks making mistakes. This should not be an A. That should be an N. We're not choosing A. That's an N. We're choosing a big capital N so that little n bigger than that capital N implies that the modulus of fn minus f is less than epsilon for all z on gamma, since we converge uniformly to f on the image of gamma, right? On that curve. All right, fair enough. Sorry about that. The textbook had a typo there that I didn't catch on my first read through. Weird. Okay, so by proposition 2.1.6, which just tells us how we can break apart contour integrals, we can take the, oops, I should use a different color than white right there. We can take the modulus of the difference of these two contour integrals, and since they're over the same contour, we can combine those together. That is, we can look at the modulus of the contour integral of the difference instead of the difference of the contour integrals. Okay, and then we can, of course, move that absolute value bar on inside at the cost of a less than or equal to sign. Okay, that's once again from proposition 2.1.6. And of course, via the fact that we have an upper bound for this piece, we can say that this contour integral right here is less than that upper bound epsilon times the length of the curve. Oh, okay, that's not bad at all. But hey, look, we can make epsilon as small as we want. The length of that curve doesn't change, so we can make this right here, this guy right here, as small as we want. So we can make this bounded by something as small as we want. Oh, this will go to 0, meaning that this thing ends up being the same as that thing. That is our first assertion right here. So we've proved it. The second assertion, like I've said before multiple times, is obtained from the first one. It is a slightly more restrictive case of the first one. We just make our fn's into partial sums. Easy. Nothing fancy going on at all. Okay, now why are we bothering with all this? What's the point? What's going on? Here's where it starts to get fun. Here's the big hoo-ah, you know, the meat of the day. Here's the beef. It's the analytic convergence theorem. This is what we've been building to in this section. Everything else is child's play. This is the real deal. And this will prove instrumental in the next two sections of this chapter. So the analytic convergence theorem is two parts, 1 and 2. As it will turn out, it suffices to prove 1, and you'll see why very shortly. So analytic convergence theorem lets us bring all the stuff we've been doing so far. It takes the pieces we've built, and we're going to carry this over into the context of analytic functions and see the beginnings of what having continuous differentiability and the Cauchy-Riemann equations, that notion we've been calling analytic, some people call holomorphic. We'll see how that tells us something about series representations of such functions. So to start it off, part 1, we're going to let A be an open set in C. Open, very important right here. And we'll let Fn be a sequence of analytic functions defined on this open set. Now, if this sequence of analytic functions converges to some function f uniformly on, and I'm going to highlight this, on every closed disk contained in A, then we get the big results. Then f is analytic. Furthermore, these derivatives, the derivatives of Fn approach f, pointwise on A, and uniformly on every closed disk in A. Okay, remember, uniform convergence definitely requires pointwise convergence, right? If you have uniform convergence, you always get pointwise, but pointwise doesn't necessarily give you uniform. So the pointwise piece is pointwise on A may be less interesting. The uniformly, big old deal. But uniformly on every closed disk in A. So that's a slight distinction. Okay. Now, see here's the picture. Here's, if you want the picture is that you've got A. It's a big old blob in the complex plane, yeah. Bada boom. And then you can always grab little closed disks inside of this guy about some point. And we'll talk about why you can always do that. But for the moment, just that's the picture. Okay, closed disks inside of A. All right. So second part of it, if GK is a sequence of analytic functions defined on an open set A, and GZ is equal to, well, the series defined by these analytic functions, right? The sum from k is 1 to infinity of gk of z. If this series converges uniformly to this function g on every closed disk in A, then g is analytic on A, and the derivative of g is given by the series of derivatives of the gk's. Pointwise on A, and I will highlight again to make it clear, pointwise on A, and also uniformly on every closed disk contained in A. And in fact, if I want to stay consistent with how I did it up here, honestly, I should have made this part blue to make it clear that I'm every closed disk contained in A, every closed disk contained in A, blah, 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 right? Okay. So if you can see, the second one is, just like before, a more restrictive case of the first one. That is, in the first one's case, we're just taking these fn's to be the partial sums in the series, right? Sum from k is 1 to n of g k of z, right? Just put that as fn, and you obtain the second one right from the first one just by using the linearity of the derivative in this little piece right there. Okay, simple. Nothing too fancy is going on. Let's prove it. This is going to be fun because we'll get to finally tie back in everything we were doing in the last chapter. All right. Now, this is verbose proof. I decided not to rewrite it just so we could have everything up on the screen, and I hope that helps a little bit for following along. So, proof of the analytic convergence theorem. So, like I said, it suffices to prove the first part, since the second part is just a more restrictive form of the first part, though it is nice to see it. We'll start by picking a point z0 in A, and we'll look at the set of z that are within a distance of r from z0. That is, it's a closed disk around z0, entirely contained in A of radius r. That is, we're choosing some r so that this disk is entirely contained in A. A good question. Why does this disk exist? Why does it exist? Ask yourself it quick. See if you can think about it. Do you see it? It's because of the first big important piece I highlighted up here. Let A be an open set. So an open set like this right here, any point in an open set, let's let this be some point, every point in an open set has a little open disk around it. No matter where you are in an open set, every point in an open set, there you can make a little disk of positive radius, of non-zero radius, about that point entirely contained in the set. Remember, if you couldn't, then it would be like a limit point or something, right? It'd be like it wouldn't be an open set. This is how we define open sets, just by having little disks around things in the sets, right? Okay, so if we can get a little open disk around it, then we can certainly get a tiny, tiny closed disk, right? That is, if all of these points in this open set are here, in this little open disk, you can always grab a smaller circle inside of it. That is, what I'm trying to say is that if you have, let me draw it slightly bigger. Oh, actually, that's kind of smooth. Oh, well, that's not going to work as well. Never mind. Oh, whoa. No, that's not what I want at all. Why is that not opaque? There we go. What I'm trying to say is if you have some sort of an open disk, which we will stay consistent with our usual method of representing by putting some little lines in the, making the boundary dashed lines. You know what I'm saying, right? Okay, so you've got boundary that's dashed lines. I probably should have drawn that later, so I have this not looking so freaking weird. God dang it. I've made a variety of mistakes doing this right here. Let's make this picture better. Here's what I'm trying to draw. Okay. So we've got some kind of an open disk here, right? Okay, all good, all good. Now we're finally back to drawing better. You can always, if you've got all these points here, you've certainly got a little tiny closed disk inside of it. Oops, I made another mistake. See what I'm saying? You can always get like a little solid circle inside of a circle that doesn't have the edges. Fair. Okay, whatever. Sorry. That was a terrible drawing. I had a lot of difficulty with that. Anyways, so such a disk exists. That is, if you've got a point z naught in A, you can always find some r greater than 0 such that you can get a closed disk in z naught entirely contained in A. This has to exist. Okay. So back to the fun of the proof. Now, this disk of centered at z naught of radius r that doesn't contain that boundary, right, is a simply connected region because it is convex. Huh, okay, convex. And in this case, if we look at this strict less than instead of this less than or equals to up here, right, then we definitely get a region. It's an open it's an open connected set, right? And in fact, it's simply connected. Okay, so since Fn converges to F uniformly, the sequence of functions converges uniformly on this set, on this disk, right? On the closed disk. Well, why does it do that? Well, since it's in A, right? Okay, it's entirely contained in A. So of course it converges there since it converges in A. Right? And it converges uniformly on both. Okay. It is then clear that Fn converges to F uniformly on, well, on the interior of the set we just asserted that it converges uniformly on, right? That is d z naught r. This disk of centered at z naught of radius r, this open disk, is certainly contained in the closed disk centered at z naught of radius r. Kind of obvious. We're being a little bit verbose right here. Okay. So we want to show that F is analytic on this little domain right there, on the disk centered at z naught of radius r, the open disk, right? To do this, we're going to use Morera's theorem. Bum, bum, bum. That was like the last thing we did in section 2.4. Okay, cool. So what do we have to show for Morera's theorem? Well, we're going to have to show, among other things, that F is continuous and its integral about every closed curve is 0. Now, by the deformation theorem, we really only need to show this for every closed curve given by like a circle, right? We don't have to do it for very crazy shapes. We can just do it for any, on the edge of any disk or something. But let's just get right into it. So proposition 3.1.6, F is continuous on this little disk, absolutely. Right? It's the uniform limit of continuous functions. We've been using that the entire class. Great. Let's grab any closed curve in this open disk of radius r, centered at z naught. All right. So since the Fn's are analytic, by assumption, then the contour integral about these fn's is 0. That's just Cauchy's theorem. And the fact, it's just obvious from the fact that this guy is simply connected, right? Okay, cool. Simple. So by proposition 3.1.9, though, which we just went through and proved a second ago, these guys converge to f. Oh. Okay, so the contour integral of the sequence of contour integrals converges to the contour integral of the limit of that sequence, right? Okay, fair enough. And since these guys are all 0, well, the thing it has to converge to is 0. Does that make sense? If you have a sequence of zeros and it converges to 0, right? Yeah, okay, good. So by Morera's theorem, F is analytic on that disk. How about that? Okay, it's analytic on the disk right there. Easy. Now, why didn't we just start with A? Why did we grab this disk? What the heck? Now, look at this. On every closed disk contained an A. Oh, okay. And F is analytic. What's going on right here? So, F is analytic on DZ not R. Let's finish the proof and address this again. So, we want to show that F, the derivative of these Fn's, converges to F's derivative uniformly on closed disks. We're going to use Cauchy's integral formula for derivatives. Remember, this let us represent the kth derivative in terms of a contour integral of a quotient with f over a given point inside of the contour minus z to a power, if you all remember that. And of course with a little adjusting factor, 1 over 2 pi I. So we're going to use Cauchy's integral formula. We'll take B to be the closed disk of radius r centered at a point z naught. Okay, closed disk in A. We can always find closed disks at any point in A. Remember that, we just started with that. So we can draw a circle gamma of radius slightly bigger centered at z naught that contains B entirely in its interior. Now they tell you to go look at some worked example, but this is a very obvious fact. So if you want to see this, we can even zoom in a tiny bit right here. This is sort of a terrible picture, but it should suffice. Pick any point on the boundary of a closed disk contained in a set A. Okay. Now, since that point's in A and it's an open set, we can always find a little tiny open circle, like an open disk around that point that is entirely within A. We can do that at every single point. We can find some little tiny disk, right? Every single point. But hey, if we can do that at every single point, that means that there's a little bit more on the outside of every single point that we could put into the disk, right? So we can grab a little bit bigger disk and still stay in A. We can always grab a little bit bigger disk and stay in A. Oh, okay, so that's all that's going on. Just using the nice properties of open sets again and again and again. Okay, so we can draw a circle gamma of radius rho, a little bit bigger than r, centered at z naught, that contains B entirely in its interior. Okay, so for any z in B, since we are containing it entirely in the interior of this curve, we can write the nth derivative of one of these functions in terms of Cauchy's integral formula as 1 over 2 pi I, integral about gamma, contour integral about gamma of fn, the given function, over zeta minus c squared d zeta. Easy. Okay. And then, of course, we can do the exact same for f. Okay. Nothing fancy. But hey, wait a second. Wait a second. Didn't we just prove something about commuting contour integrals with series or contour integrals with sequences? Oh. We've got a sequence of contour integrals. How about that? So this just comes from the Cauchy integral formula, and by our hypothesis, Fn approaches F uniformly on the closed disk consisting of radius r, the closed disk of radius rho, right? Remember, rho is a little bit bigger than r. It's the circle, right? The circle gamma, or it's the boundary of it at least. So we've got this disk, okay, that lies entirely in A, since we've constructed it like that. See our little pictures before, and we've got uniform convergence on A. So for any epsilon greater than 0, or for a given one at least, we pick a capital N such that little n greater than or equal to big N implies that these guys, they are within epsilon of each other. That is Fn of z minus f of z in modulus is less than epsilon for all z in the disk. We can do this because we have uniform convergence. Bada boom. That's what uniform convergence is all about. Since gamma is the boundary of this disk, just by construction, that's how we built it, right? For n, little n bigger than big N, this implies that Fn of zeta minus f of zeta in modulus is less than epsilon. It's the exact same statement right here, but I just replaced the symbol z with a zeta. Oh, okay. And that's just on gamma. So for zetas on gamma, of course it holds. If it holds on all of the closed disk, it certainly holds on its boundary. Easy. But hey, actually write down what we've got for the derivatives right here. Well, look, we've got, just use the fact that we're doing a contour integral along the same curve, gamma, and we can put these two together, right? We get Fn minus f. They've got the same denominator. Easy. We get 1 over 2 pi I, contour integral about gamma of Fn zeta minus f of zeta all over zeta minus z squared d zeta right there. How about that? So for zeta in gamma and z in B, zeta minus z is greater than or equal to rho minus r. Okay, wait a second. What does that mean? Zeta minus z is greater than or equal to rho minus r. We have to go back and look at rhos and r's, right? Rho minus r. Rho is the radius of the circle gamma. It's a little bit bigger than r, right? Okay. Now everything in this little disk is within r of z naught, right? So how far away could they be from each other? Well, the biggest difference right here could be to the center of the circle, and then, you got the little rho, right? Okay, so rho minus r. Does that make sense? If it doesn't, just draw the picture. You will immediately go, oh, okay, obvious. It just, I don't want to belabor the point too much. So we are almost at the end of class anyway. So we've got, say, like r, and then let's write this one as rho, right? So rho minus r, what is that distance? It's like right in there, right? This distance right here is rho minus r. Yeah? So it's the distance between stuff, it's as far away as you can be in there. Okay. Anyways. Zeta minus c, rho minus r. Okay, simple. So for n greater than or equal to big N, this implies that, well, just plug right in here. This guy, less than or equal to, hey, 1 over 2 pi. The I was, doing a modulus, so you get rid of it. Okay, epsilon, well, that's just from up here. And then the bottom, rho minus r squared times the length of that curve gamma. We're just using, once again, this bounding theorem from chapter 2 that we keep using. That is, if we have a bound on the integrand, you just take that bound and then the absolute value, take that bound times the length of the curve. Easy. Okay, so there we go. And we just have epsilon, which you can make as small as you want. And then all of this right here, notice these guys are all constants. So product of a bunch of constants, still just going to be constant. Something as small as you want times something fixed, you can still make as small as you want by choosing the epsilon, potentially smaller if we need to. All right, easy. So this guy we can make as small as we want. meaning that these guys can get as close together as we want them to, meaning they converge. Okay. Rho and R are fixed constants independent of Z, so we get the desired result. Bada boom. Okay, let's return a little bit to look at this top piece right here. Obviously, 2 going to come from 1, but let's talk a little bit more about 1 really quick. So A being an open set, that was of key importance. That was a very big deal. Okay. Now we had a sequence of analytic functions. We didn't really use analyticity very much, did we? We used it a little bit. We used it for the piece involving Koshi's theorem right here, where we showed that these contour integrals were 0. And this let us use Morera's theorem to get the analyticity of f. So all we used the analyticity for of the sequence is to get the analyticity of the result. The uniform convergence was used very heavily. This is a big old deal, but the part that maybe feels a little bit foreign is the fact that we're doing this for every closed disk contained in A. Now, the reason we're doing this is for Morera's theorem. That is, we need to get the bound that comes from uniform convergence for every closed disk in A to have everything work out right with the derivatives. Now, we also need it just because Morera's theorem requires, if we want exactly the same way as, there we go, I've got it, I think. Oh, there's that long proof right there. There we go. Morera's theorem. Okay, so if f is continuous on a region A, and the contour integral about gamma of f is 0 for every closed curve in A, then f is analytic on A, and little f equals the derivative of big F for some analytic function f on A. Okay, this was kind of the converse, right? So we needed this this piece right here to hold for every closed curve in A. Now we're doing that on every, by using the bound we get from uniform convergence, we're able to do this here. We do it for a gamma a closed curve in this little disk of radius r right there. Okay, and so we just pop that on through, easy. The sorry, I feel like I'm confusing things more here, but hopefully everyone sees the idea is that we're just taking Koshi's theorem and using it along with some of these nice results about uniform convergence and saying, hey, uniform convergence preserves analyticity in at least locally, at least in closed disks, right? And it converges. It brings pointwise convergence all over and uniform convergence for derivatives as well. So if you have uniform convergence of analytic functions, you get analyticity on closed disks, and you get uniform convergence of derivatives on closed disks as well. Okay, kind of cool, kind of nice. What will we do with this next time? That is probably the big question, because that's pretty much the end of this section. Next time in a lecture, I am still in the midst of making kind of a lot of pieces to click off here. There we go. We'll talk about power series and Taylor's theorem. Oh, everyone knew it. Everyone knew we're building to Taylor's theorem because we liked using that in Calculus 2 so much, and all of the results we talked about in the first piece of this chapter are good old-fashioned Calc 2 results, and we sure love Taylor's theorem in Calc 2. So we're going to talk about power series. We're going to talk about representations of analytic functions via power series, and it'll give us a lot of cool things. So we'll get to that next time, and we'll call it quits for today. Just an FYI, I'm going to post the next lecture not on Friday. I'm not going to stream it, or I might post it on Friday. I might set the announcement to delay till Friday, but I'm not streaming live on Friday. I'm going to record it at a different time because I have to take a trip out of town to visit my grandma. So, yeah, so if you are one of the people who watches live, don't expect to see it on Friday. And yeah, but the video will be posted and everything, so no interruption or cancel class. But yeah, awesome. That may slightly slow down my grading of the exams too, being out of town, but it shouldn't very much. So, all right, let's call it quits for today, and I hope you have a great night. See ya.